So we're continuing looking at the same problem. Even if you hadn't watched the first video, this will still all hold together by itself. In the first video, we talked about a and b. But we got this function, f of x is x squared times 3 minus x, which we expanded into 3x squared minus x cubed, because sometimes that's useful for doing derivatives quicker. Next, what we're interested in is finding when f is increasing and decreasing. And pretty much at the same time, we're going to be identifying local extremes. So for increasing and decreasing, we're interested in where is the derivative positive or negative. It's the easiest way to be doing these problems. You can talk increasing, decreasing without derivatives, but it's far easier when you do have them at your disposal. So we've got f of x is 3x squared minus x cubed. And really what this is asking us is when is f prime of x positive or negative? Mean value theorem is actually the machinery underneath why a positive derivative and a negative derivative definitely implies increasing and decreasing. But intuitively, a positive derivative is something that should have a positive slope. A negative derivative is something that should have a negative slope. That looks like that's going up as you move to the right, moving down as you move to the right. So we need to find f prime. F prime of x is 6x minus 3x squared. We want to know when that's positive or negative. And so having this in a factored form is going to be nice, because in the times it switches from positive to negative or vice versa, it's going to be hitting 0 or it will be undefined. Well, this is never undefined, so it'll be hitting 0. Factor that. That's not 2x, but rather 3x. 2 minus x equals 0, and so it's potentially going to switch at 0 and 2, the critical numbers. They serve a double purpose. They're both places where absolute extremes might happen, that are also places where increasing and decreasing might change. So I'm going to mark those down here on a number line that I label with an f prime. And I like to label at 0 and at 2, my f prime is 0. I'd put a little u there if the derivative were undefined, just to remind me something weird happens. But then the nice thing about this is f prime is only ever 0 at 0 and 2, which means between 0 and 2, it's going to be either all positive or all negative. So whatever it's doing at one value is going to be doing everywhere. So f prime of 1 is going to be 3 times 1, 2 minus 1. So that's a positive number, 3 times 1, 3. I don't really care about the 3 so much as the positive of it. Positive. So what that tells me is that in between 0 and 2, f prime is positive, which means my original function, f, is increasing. And I can continue on. And it doesn't matter, at 1 it's positive, but also everywhere between 0 and 2. F prime of 1/2, f prime of 3/4, f prime of 1.9987. It's all positive there. I only have to check one test value. So, f prime of 10, I like to pick big numbers when I'm out on the ends because they're a little easier to work with. I'll use this version of f prime for here. That's 60 minus 300. That's a negative number. That's negative 240. I don't care what number. I care about the negative part, though. That's minus, and then likewise for the far left, negative 10. That'll be negative 60 minus 300. That's also negative. So in the end, I get this minus plus minus structure that tells me that my original function f from 0 to 2 is going to be going up, down, down. Remember, increasing, decreasing is always left to right. Because we're interested, as you put a larger x value and as you move farther to the right, does your output get bigger or smaller? So it looks something like this. We're talking increasing on from 0 to 2 and decreasing from negative infinity to 0 and from 2 to infinity. Some books, I know WebAssign does this, for example, insists that you write it with a union sign, even though technically decreasing on an interval is only defined for an interval, and this union is not an interval, but minor technical point. It's decreasing for these x values and for these x values. It's based purely on this, we already have the extreme values, the local extremes. This looks a lot like a minimum, this looks a lot like a maximum, and this is exactly what they are. First derivative test tells us if the derivative is switching from negative to positive, or from positive to negative, that is enough to say, yep, that's the maximum, or yep, that's the minimum. Sometimes I'll drill down, up, down, just to sort of keep myself straight as far as I switch from positive to negative or negative to positive. I get that mixed up, so I like to draw it. I'm not going to mess that up. We've got a local minimum at x equals 0 and a local maximum at x equals 2. Now this is one of those things, how you answer a question like this varies depending on the book that you're using, who is asking your question, and instructor preference. For Stewart, they tend to ask for the x values for local minimum and the x values for local maximum, and not so much the actual value of the function itself. They only want the address, not the actual height. Whereas for absolute extreme and the absolute extreme values, they're looking for the y values. It's weirdly inconsistent. It's just the way it goes. For inflection points, they want both. Go figure. That's C and D on this sheet. That's where's f increasing and decreasing, and where are the local extremes. I'll do the other parts in the next video.